Where is the S block in the periodic table? It's the first two columns or groups of the periodic table. This region of the periodic table is sometimes referred to as the S block because all the outermost electrons of these elements will occupy the s orbital. There are two columns in the s block because an s orbital can hold a maximum of 2 electrons. The metals in group 1 include lithium, sodium, potassium, rubidium, cesium, and francium. Note that hydrogen is not included here, as it typically does not exhibit metallic behavior. Here are some interesting facts about the group 1 metals. Lithium is the most abundant member of the family. Francium is radioactive, and its longest-lived isotope has a half-life of only 21 minutes. Do you know the origin of the group name alkali metals? When group 1 metals react with water, they produce hydroxide OH ions. Hydroxide ions in water produce basic or alkaline solutions. In the presence of phenolphthalein, an indicator, the solution will turn pink as hydroxide ions formed react with phenolphthalein. Before we move on, let's review the electron configurations of the alkali metals. Lithium, with only 3 electrons, has a configuration of 1s2, 2s1. Sodium, with 11 electrons, has an electron configuration of 1s2, 2s2, 2p6, 3s1. Similarly, for potassium, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. They all have something in common. All the electron configurations end as s1. This is emphasized when the electron configurations are written in noble gas notation. All the alkali metals have electron configurations that end as ns1, where N is the highest occupied principal energy level. With such similar electron configurations, it's no surprise that the alkali metals have some very similar physical and chemical properties. We'll explore these further as we go through the module. The group 1 metals are the most reactive metals known. In fact, they are so reactive that they are never found in their elemental state in nature, only in compounds. Since they all react with water, they must be stored under oil, as shown in the illustration. They will even react with water in the air. The alkali metals are all shiny and silvery in appearance. They are so soft that they can be cut with a table knife, which is often surprising to students. Like all metals, they are good conductors of both heat and electricity. As shown in the diagram, they will form a dull oxide layer on their outer surface when exposed to air. This layer can easily be cut away to reveal the shiny interior. Recall that the alkali metals all have electron configurations ending as s1. The single valence electron for each of these elements is relatively loosely attracted to the nucleus. If this sole valence electron is lost, then the resulting ion is isoelectronic with the preceding noble gas elements, that is, having the same number of electrons as the preceding noble gas. Thus, the typical ion formed by alkali metal is a cation with a charge of +1. Let's go on and review some periodic properties as they relate to alkali metals. As you consider the group of 1 elements from top to bottom, atomic radius increases. This can be explained because as you move down the group, there is increase in the number of shells and therefore the atomic radii increases. The cations that form are in all cases smaller than the parent atom. Since there are fewer electrons, there are fewer electron-electron repulsions, and so the radius is smaller for the cation. For essentially the same reasons as we discussed with atomic radius, the cation radii for the group 1 metals increase from the top to the bottom of the group. As shown in the graphic, moving from left to right across a period, the alkali metals have the largest atomic radius of any element in the period. Try to answer this question on your own before you proceed. Where in the periodic table would you expect to find elements with the largest atomic radii? The largest atoms are found in the lower left-hand corner of the periodic table: cesium and francium. Recall that ionization energy is defined as the energy required to remove the outermost electron from an isolated gas phase atom. Since the valence electrons are significantly shielded from the nuclear charge, the ionization energies of the alkali metals are relatively low. In general, ionization energies decrease down a column, and the alkali metals are no exception, as shown in the graph. Enthalpy of solvation or hydration energy is the amount of energy released or absorbed when 1 mole of an ion is dissolved in a large amount of water. In general, as the ionic radii get larger, hydration energy decreases, and so the enthalpy of hydration decreases from lithium to cesium. One result is that lithium salts, unlike the salts of the other alkali metals, often form hydrates such as lithium chloride dihydrate. How can we test for the presence of alkali metals in a particular sample? One simple and qualitative test is the flame test. If a small amount of a metal salt is held in a flame, characteristic color changes can be observed due to the movement of electrons. Electrons get excited to higher energy levels from the heat of the flame and emit energy as light as they return to their ground state. For a quantitative test, atomic absorption spectrometry can be used based on the same fundamental principles. Let's look at the result of some flame tests. Lithium gives a cheerful candy apple red color. This yellow color is characteristic of sodium. You may have observed it if a boiling salt water sample spills over when cooking on a gas stove. Potassium flame tests emit a lilac-colored flame. Let's apply our knowledge to a problem. An explosion occurred in a chemical storage tank at 𝙁𝙗𝙃 Chemical Company. An employee, while filing a claim for workers' compensation for injuries, states that the potassium nitrate being stored in the tank must have been responsible for the green flames he observed. Is the employee being truthful? We just learned that the presence of potassium gives a lilac flame. Therefore, we must conclude that the employee is not being truthful. Let's discuss some chemical properties of the alkali metals, starting with their reactions with oxygen. They all react vigorously with oxygen. They don't all form the same kinds of oxides though. Lithium reacts with oxygen to form a simple oxide, Li2O. Sodium forms sodium peroxide, Na2O2. The other metals all form superoxides. For example, CSO2. The oxides and peroxides that form from the alkali metals are typically white solids, as shown in the illustrations. They are basic anhydrides when placed in water. They will generate hydroxide ions, and thus basic solutions as shown in this reaction for lithium. The alkali metal superoxides, which only form with the larger alkali metals, are typically yellow or orange in color. Let's try some problem solving. What is the oxidation number of each element in the compounds? Lithium oxide, sodium peroxide, and rubidium superoxide. Recall that the sum of the oxidation numbers must be 0 for a neutral compound. For lithium oxide, since each lithium ion must have an oxidation number of +1, the oxygen ion must have a charge of -2. Using similar logic, since each sodium ion has an oxidation number of +1, each oxygen in the peroxide ion must have an oxidation number of -1. Rubidium here has an oxidation number of +1. So, each oxygen in the superoxide ion must have an oxidation number of -1/2. As was mentioned earlier in this module, the alkali metals all react with water. These reactions release hydroxide ions and hydrogen gas, as shown in the equation here. The reactions become increasingly more explosive down the column. The alkali metals all react with hydrogen. These reactions produce metal hydrides, which are ionic solids with high melting points. The alkali metals react very vigorously with the halogens. One classic example shown in the photo is the formation of table salt, or sodium chloride, from sodium metal and chlorine gas. The alkali metal halides are crystalline solids, as shown in the photograph. They have characteristically high melting points and are soluble in water. These are very stable compounds, as evidenced by their large negative enthalpies of formation. Since the alkali metals have a high tendency to lose their valence electrons, they oxidize readily. When they oxidize, they cause some other substance to become reduced. And so, we can say that alkali metals are good reducing agents. Remember, the substance that is oxidized in a redox reaction is called the reducing agent. The alkali metals will dissolve in liquid ammonia. As the metals dissolve, the resulting solution turns blue, as shown in the photograph. The blue color is due to ammoniated electrons, which absorb visible light. The solutions are paramagnetic, which means that they are attracted to an externally applied magnetic field. When allowed to stand, the solutions slowly release hydrogen gas as amides are formed. as shown in the reaction. When concentrated, these solutions turn a bronze color and become diamagnetic. Let's go on and discuss some uses of the alkali metals. Lithium alloys are used for a variety of purposes. An alloy with lead is used to make engine parts. An aluminium-lithium alloy is used in airplane construction. And a magnesium-lithium alloy is used to make armor plates. Lithium metal is used in some thermonuclear reactions and to construct various types of batteries. Liquid sodium is used as a coolant in fast breeder nuclear reactors. At one time, a sodium-lead alloy was used to produce organo-lead compounds, such as tetraethyl lead, which was used as an anti-knock agent in automobile fuel. The use of leaded gasoline was phased out due to the environmental pollution that it caused. Potassium has a variety of roles in biological systems. Potassium chloride, sometimes called muriate of potash, is used as an agricultural fertilizer. Potassium hydroxide is used to make soap and to absorb carbon dioxide. Cesium is used in the manufacture of photoelectric cells. In subsequent modules, we will discuss important compounds of the alkali metals and their biological roles.